Hello, everybody, and welcome to episode 27 of I Wish You Were Dead, a podcast about things that used to be alive. My name is Mike, and that is Gavin. Gavin, I feel like 27 is significant, but I don't know why.
Yeah, I got nothing.
Yeah, neither do I.
I
It
don't
feels
know.
like it feels like a cool number, though.
I don't know. Like, it feels like vaguely significant for some reason, but I'm sure it isn't. I'm sure it only seems that way now since you said it.
Yeah, right. I have put that into your head.
Right, and I don't like it. Anyway, welcome.
Welcome, everybody. So I think we're going to get right into the show today, if we can. Just a couple quick announcements before we get started. Once again, we have a Twitter account. You can follow us on Twitter, where Gavin will retweet a whole bunch of different things and put out some original tweets. You've been a little more active on there over the last couple of weeks, from what I remember. Is that right?
Absolutely. I've been finding lots of really neat, like, open source type articles. So if you want to read about, real paleontological research without having to be affiliated with, like, a university or having to pay to get past whatever company's paywall, follow us on Twitter and check out some of the interesting articles that I've been tweeting out.
Absolutely. And that is dead podcast underscore at dead podcast underscore. We have
Absolutely.
those same forms that we always have, where you can go ahead and request a topic or tell us about a specific guest that you want to check out. And of course, we have Gavin's blog that hopefully will be coming out of hibernation very soon.
Hopefully, yes. So we mentioned last week, or maybe 2 weeks ago, I'm not sure. Mike and I both volunteer for a youth leadership organization. I do more than one weekend of it, though. So I'm in between my second and third of 3 weekends right now. And the one coming up is the one where I have most responsibilities. Yeah, it's been a very busy couple weeks. Ideally, sometime next week or the week after, there'll be some new activity going on. It will be de-extincted, I guess. The blog will. So
it will be back from the dead. So those are just some quick updates. We don't plan on doing those at the beginning of every show, but we just wanted to make sure those get said right up front now.
Absolutely.
And so before we actually get in the show, we have to go ahead and talk about this week in science. So we're going to take a look here. Gavin's got the calendar. I'm going to go ahead and guess we are taking a look at something from the year. I'm going to go out on a limb on this one. I'm not feeling very confident, but I'm going to say 2013.
No, this is one of the older ones that I've seen from this calendar. So this is from June 17th. So tomorrow, if you're listening to this the day it comes out, but of 2009.
Wow, I thought 2013 was going back a ways, but all right.
So the headline is Nutcracker Dinosaur Discovered in Gobi Desert. It's always interesting, and like I haven't fully read the little paragraph here, but it's always interesting when we find a new dinosaur or new anything, realistically, doing something that you don't expect it to do, or it's at least interpreted to be doing something that you don't expect. So let's dig a little deeper, shall we?
Let's do it.
So the paragraph says, paleontologists from the University of Chicago announced the discovery of a unique species of dinosaur, the remains of which they said were found beneath the sands of the Gobi Desert in Inner Mongolia, which they don't actually say, but Inner Mongolia is actually not in the country of Mongolia. It is actually a province of China.
Really?
Yes. They don't specify that, but it is like an autonomous province of China, so it has much more self-governance than some of the other provinces do. But
the more you know.
It continues. Interestingly, experts say the dinosaur was the first on record they thought to consume a diet of primarily nuts. Dated to the mid-Cretaceous period, or nearly 110 million years old, scientists say that the dinosaur possessed an abundance of gizzard stones, which it used to grind and digest tough objects such as nuts and seeds. Additionally, the angle of the dinosaur's jaws represented a type of chewing mechanism that paleontologists say may have gone unrecognized in other related herbivorous dinosaurs. They don't actually give what the species is, though.
That seems like an oversight.
Right, like they don't give the name of it. But
we should make our own calendar.
We should, just because, like, I don't know. This one it's provided us with some good ammo, but like it's also lacking quite a bit in a few places.
Yeah, it was, it is a solid place to start, but you'd think that, yeah, stuff like that, like the actual species of dinosaur, you'd think they'd be able to cover.
Yeah, right? Like that's the thing that most people care about. Where it's like, oh cool, this nut eating dinosaur. What's it called? Oh, I don't know.
Right. Gonna Google nut eating dinosaur. I'm a little worried what that's gonna turn up on Google, but
Yeah, be careful.
yeah. Not only will I be careful, I will not be doing it. What we will be doing is getting right into today's episode. So today's episode is one we have sort of teased and hinted at, I think, in different ways since really the start of our podcast together. So, Gavin, what is it that we're going to be talking about today?
So I want to preface this with a couple things. Number one, this is not going to be an episode really about climate change. This is going to be sort of the required reading before we do that episode eventually. It will come, probably not in like the immediate future, like it won't be next week. But yeah, so this is some of the background about fossil fuels and why they are bad. Because for the climate change episode, I'm going to talk about climate change throughout history and how it is relevant to the climate change going on today. So that's sort of the layout for the future. The other thing that I wanted to preface this with was that this was actually requested by a friend of the pod, my girlfriend Liz, just a couple days ago. So
very good friend of the pod. No, I mean, this sounds like it's going to be the sort of like the precepts. Like you have to, in order to be able to talk about climate change, you have to understand like what fossil fuels are. Like we've talked, like you've probably heard about fossil fuels your entire life, but and we've heard that they're bad. But like, why are they bad? How does that actually work? And I know that's something that even for me, like I am aware fossil fuels are bad, but it'll be good to have a more firm understanding of exactly how that works.
exactly, and so some of the main things we're going to go over in this episode is why they're called fossil fuels, what are they made of, and why aren't they renewable? Because if they're made out of fossils, presumably they're made out of dead things. Things die all the time. Why aren't they renewable? And we're going to talk about, there are many different kinds of fossil fuels, but the three that we're going to talk about today are probably the three biggest ones that most people have probably heard about, which are oil or petroleum. I'm going to use both of those kind of interchangeably. They mean roughly the same thing.
Mm-hmm.
Natural gas and coal. So some things that all three of these have in common is that they are formed from hydrocarbons, which are kind of exactly what they sound like. It is a carbon atom with hydrogen around it. So hydrocarbons are unique in that, so if you think way back to like high school biology, you might know the chemical formula for sugar or glucose, which is...
Ooh, this is coming to my... Wait, can I try?
Oh, yeah, go ahead.
If I remember correctly, this I don't know why this is burned in my brain, but I think it's C6H12O6.
You are absolutely correct.
Oh yes.
So that is not a hydrocarbon because it is not just carbon and hydrogen. It's got the oxygens in there, which make it a different class of molecule.
Right.
So carbon is a really neat element, and it's neat in ways that make it useful for life. There's a reason why all life on Earth is carbon-based, quote unquote. So carbon, there's going to be a really...
I'm sorry, have you ever seen the movie Jimmy Neutron movie?
Of course I have.
Do you remember the part at the end for no reason they're like, we're carbon-based life forms?
Mm-hmm.
I've never quite understood what it meant to be a carbon-based life form, but that was always funny to me.
Basically, every kind of macromolecule that we use uses carbon as its base, with like one or two exceptions. Obviously, I'm not like a biochemist, so don't come for me. But
broadly speaking, carbon is in every molecule we're going to be using in some form or another.
Pretty much, unless it's like an isolated ion that we use. We use a lot of different ions for things, but carbon is essential to every form of life. Everything from us to plants to just like single-celled bacteria. Everything needs carbon. And there's a particular reason for it. So I'm going to do a little bit of very basic kind of chemistry stuff here. So this is kind of, high school chemistry / maybe even like middle school science. I don't remember. But so an atom has its nucleus, right?
Yes.
And that has two types of things in it. There are protons and neutrons. They make up the nucleus, the center part of the atom. And then you have what's frequently drawn as just like rings of electrons around it. It's much more complicated than rings, but that's just a simple metaphor, so we're going with it.
Right.
They typically always draw the first ring, the closest ring to the nucleus, as having only 2 electrons, with the exception of hydrogen, because it only has 1. But what's convenient about that is that every ring outside of the first one has 8 maximum electrons.
So that first ring, like that, it can fit 2, and then each subsequent ring can fit a maximum of 8 electrons.
Right.
Okay.
And depending on how many electrons it has in the outermost ring determines if it likes to steal electrons from other atoms or give away electrons to other atoms. So for example, if its outermost ring only has 1, it wants to give that away because it wants the outermost ring to be full. And if it gets rid of that 1 pesky electron, then its outermost ring, which is the one, inside from that, because that ring is now gone, because that electron's gone, is now full.
It was always my understanding this is why we always referred to oxygen as O2, because oxygen doesn't like to be by itself. It always wants to be bonded with literally anything, including itself.
That's a different kind of bond, but same idea, yes.
Okay.
But carbon's in a really neat spot because carbon has 2 in the inside loop, like in the inside ring, like it's supposed to.
So that one's full.
And then in its outermost one, it has 4.
So it's half full.
It is.
Okay.
Which means it is essentially, for all intents and purposes, the math doesn't, it's slightly off, but it is essentially equally likely to give or get electrons, which means that it can bond with almost anything.
That seems like advantage is probably the wrong word, but like that seems to actually make some sense as to why we see carbon in just a whole bunch of different, molecules, a whole bunch of different substances. You always see carbon hanging around.
Right, and don't get me wrong, like there are other elements that have that too. Like for example, let's see, what would be 8 above that? So that would be the whatever element number 14 is. I don't know the periodic table as well as I used to. Element number 14 would be the same scenario, but because carbon A is much more abundant than whatever that is, the fact that I don't know what it is off the top of my head probably is kind of indicative of that.
I am looking it up right now.
At least if
silicon.
Is it silicon? Which,
yes,
that also makes sense. Silicon is also extremely common, not nearly as common as carbon is, at least in life. But silicon has like an extra ring to it. So, but because it's like the closest ring to the atom that can have 8, makes carbon, again, much more likely to give or get, and much more willing to, because closer to the nucleus of the atom, is positive and electrons are negative, so they want to be close. So if you try to fill the closest one, that inherently makes it more attractable to electrons, if that makes sense.
Mm-hmm.
But so carbon is a really unique element in that way, and it makes it really easy for it to bond to a lot of things. But frequently, as we're talking about today, it bonds to hydrogen, and then also it really likes to bond to other carbons. It likes that a lot. And so some of the really common hydrocarbons are things that you've probably heard of but didn't know were this. So that would be things like methane.
Oh.
Methane is 1 carbon surrounded by 4 hydrogens. Because the 4 hydrogens each have 1 electron. They give that to the carbon, and then the carbon's happy because it's now full. Some other common ones are propane.
Oh, okay. Lots of
Propane,
gases.
yeah, propane is a string of 3 carbons, all surrounded by hydrogens. Butane, which is lighter fluid, that is 4 carbons in a chain. And then octane, which, as you might guess, is 8. So these are very common, and if you notice something about those 4 compounds, they're all highly flammable. That's
Yes.
kind of what they're known for. Use propane in
Right.
your grills, you use butane in your lighters, use octane in cars, I guess. I don't. That
Not a
one's
car guy.
mostly used like in neither am I. Some kind of fuels, like you'll see it on like the uh, gas station, whichever like thing you hit for whatever kind of gas you want. It'll say whatever kind of octane gas, and that's for reasons that we're going to talk about in a little bit. So let's sort of get into it. So now we're going to start breaking down these 3 different kinds of fossil fuels that we're talking about today. So Mike, we'll start with oil/petroleum.
Okay.
What do you know about oil?
So not much. It's my understanding that it is generally liquid. It is made from organic. So this is for those of you that don't know how we do this. I don't actually know the answer here. I am doing my best to guess. Um, but so liquid, made from organic material that has spent thousands, if not millions, of years, um, being either compacted or decomposing or going through some sort of substantive change, generally underground. I don't know. I don't think I know much beyond that, other than again, liquid made from organic material, but it takes an incredibly long time to actually undergo that process.
I mean, those are all the important points,
Okay.
realistically. Um, but some of the biggest things about oil is just to make it slightly more like relatable. Some of the things we use it for,
Hmm.
because we use petroleum in some form in almost everything, at least like here in the United States. So things that are derivatives of crude oil is sometimes, as you'll hear it, is like the unrefined version, but it's
Okay.
used for things like gasoline, diesel, jet fuel, plastics, lubricants such as your motor oils, things like that, waxes, as well as asphalt.
That's a
So
rather wide range of things that it's all used
plastic is used in nearly everything.
in. Quick sidebar: somebody was talking about, besides the internet, what's really changed between now and the 1950s or the 1920s? And I was reading somewhere it was like, if you say that, you don't understand just how much plastic has taken over the
Mm-hmm.
planet. Just how plastic is in. If you look around and you're like, oh God, plastic is everywhere.
Yeah, and I'll talk a little bit about plastic toward the end, but that's not the main focus of what we're talking about in this episode. Um, but those are some of the main things that petroleum is used for. So a really common thing that I see as usually like a meme or something, teachers who like to be fun will like put memes on like their door, like start like off their lectures with a slide of a meme or something.
I guilty as charged.
Right. So some earth science teachers probably have used or at least seen some kind of meme that is something to the effect of dinosaurs being turned into oil.
I can imagine any number of memes that that go about this.
Right. There's one particular one that I have in mind that's like a dinosaur being turned into like a plastic toy dinosaur, which haha funny meme, but like no.
Oh, okay.
um by and large, animals do not get turned into oil. It's not like impossible, but it's not by far the most uh common source of oil.
Animals don't get turned into really.
Mostly
Okay.
because there's not enough of them. They
Okay.
don't
I've
have
been lied
enough
to.
organic material because so oil forms in ocean environments. Oil will not form from a terrestrial environment.
Mm-hmm.
And deep ocean and the super deep parts of the ocean are basically a desert. There's just not enough animal life there. But
Okay.
what there is a lot of, if oceans are functioning properly, lots of little tiny itty bitty microorganisms.
Right.
Things
Like the
just
single celled and small organisms.
Right, things like algae that do photosynthesis, and then there's also zooplankton, which eat those that are also microscopic in size, but they eat the microscopic plant things. So those are, by and large, what makes oil. If a fish happens to die and fall in with those, yeah, that'll probably turn to oil too. But it's not like that's the main component of oil.
Wow. Okay.
Um, So, like I said, I'm going to walk you through basically how oil forms. And this is greatly oversimplified. There's a lot of weird geochemical things that even I don't truly understand, but this is very simplistically how it works. So, basically, millions and more likely billions of these little microscopic guys, most of whom do photosynthesis, but of course, like I said, there's things living among the photosynthetic ones that eat the photosynthetic ones. They all die and then sink. And one some of them will make it to the bottom, just statistically, because there's billions of them, especially over the course of millions of years. And some of them will decompose on the way down. Probably most of them will decompose or get eaten by something on their fall from the surface to the seafloor.
Mm-hmm.
But given the timescales that we're working with here and just the sheer amount of them, a lot of them are still going to make it to the bottom. And the bottom of the ocean is really anoxic, which, as it kind of sounds, it means that the water has very little oxygen, which makes it really good for preserving things. Meaning
Okay.
that there's, things being decomposed uses oxygen. But if the amount of things falling into the bottom of the ocean is faster than the decomposers can decompose, not everything is going to get decomposed.
Makes sense.
So over time, and we're talking, hundreds of thousands to millions of years, all those little tiny single cells will build up and then eventually get covered with some kind of actual sediment, clays, sand, stuff, something like that.
Mm-hmm.
And all the pressure of A, the rock, but also B, just all of the, all those cells laying on top of each other, all those like organisms and their dead, lifeless cell bodies laying on top of each other puts a lot of pressure on them. And so it compacts them into something called kerogen, which is technically, to my knowledge, not a rock, but you'd be forgiven if you called it a rock. It is a rather hard substance that is not really like uniform in its hydrocarbon content or its chemical structure, but it's basically just like a really compressed mass of all of these dead cells.
Okay, so it looks like a rock, but it's not technically a rock. It's just a whole bunch of dead cells that have been compacted together.
Right.
That sounds like a sedimentary rock. Am I off?
It would be. It's different from things like limestone in that limestone. So one of the definitions of a rock is that it needs to be made out of a mineral,
Okay.
and minerals, one of the definitions of a mineral is that it needs to have a like clear chemical structure,
Okay.
which kerogen does not. Kerogen is very irregular. It's not like if you take kerogen from one place and compare it to kerogen from another place, they'll be the same. Whereas if you take quartz from one place and quartz from another place, there might be very small chemical inclusions that are different between each of the two quartz crystals, but they'll still be like 99.99% SiO2. Whereas
Hmm.
kerogen varies a lot. But one thing that kerogen always has is really long chains of the hydrocarbons, not sort of the nice, neat, just like a handful of carbons surrounded by hydrogens. They'll do some weird things with making rings with the carbons, which is a more stable structure, but not as flammable because it is more stable.
Mm-hmm.
So if you were to try to burn kerogen, like it'd probably burn, but it would not burn nearly as efficiently as like methane would.
Okay.
So that would be like if you like interrupted it, or there's a really big uplift event that lifted it up too soon, you would just get an exposed bed of kerogen, and then that would all erode and go back into the carbon cycle. But if you keep pushing it down and down and down and under more pressure, all of those more stable bonds will break in the kerogen, making the smaller, less stable versions of the hydrocarbons, things like the methane, the propane, the butane. And it's when it gets to that point, it becomes much more liquid-y. Because you think methane is a gas, but things like propane and butane, you can keep, if it's pressurized, in liquid form pretty easily.
Right.
So when it breaks down into the simple hydrocarbons, it becomes more liquid-y, as opposed to the kerogen, which is more solid. When it becomes more liquidy, it can now sort of seep into some of the gaps in the rock that was put on top of all that dead stuff.
Right. It can fill in the cracks.
Right. Or in some cases, if the rock on top of it is a sandstone, there's gaps in between the sand grains that are
Mm-hmm.
fairly big, which is why all of the have you ever heard the expression like tar sands?
I have heard that expression and I haven't thought enough to actually know what it means.
That's what that is. It's essentially a sandstone unit where there's a ton of oil in it in the spaces between the sand grains.
Mm-hmm. Okay.
And if there's not too much in the way of like really solid rock layers, if it's just a bunch of sandstone, all that oil will eventually seep to the top and eventually be broken down by something eventually. Some kind of microbes. There are microbes that can break down oil. It takes a really long time, but they can do it. When it becomes really useful, and what people who look for oil look for, is what's called a cap rock. It's usually a layer of something like a shale, which is much harder to go through than a sandstone. And especially if there is sort of a fold, which makes sort of like a frown type, like a hill, basically, in the
Mm-hmm.
rocks. Because as we've talked about, rocks can be folded and bent up in all sorts of weird ways just by the continents moving around. And so what the best conditions for finding oil would be a cap rock layer of some kind of shale on top of one of these tar sand type units that has been folded to make sort of an A type shape. Because what that does is, as the oil becomes more liquidy and becomes warmer because you're pushing it further down into the earth, it'll become less dense and rise to the top of that layer until it can't go through the cap rock anymore, and it'll sit at sort of the top part of that A shape and make a reservoir. Does all that sort of make sense?
It's it makes sense. You went a little fast, but I think I have the basic idea.
Okay. But just to reiterate, just so everyone, on any potential listeners are also on the same page. You've got your layer of dead stuff, some sediment on top of it, that as the dead stuff is pushed down, it becomes more liquidy and more concentrated as the useful to humans kind of hydrocarbons. If there is a layer on top of that the liquidy oil can't go through, the oil will try to rise, but can't, and get stuck on the bottom of that layer and get trapped in like a big pocket of oil. And that's what people who drill for oil look for.
Right. So as the organic stuff falls down, becomes more liquid, gets more compressed under different layers of sediment, they will kind of naturally form for lack of a better term, I'm going to call it a bubble
Yeah,
of oil that can be eventually found and drilled and used for humans. Is that about right?
pretty much.
Now I have one question.
Yeah.
What happens if there's more organic stuff that continues falling? So it's not just, layer of organic stuff and then, more things on top. It's, organic stuff is falling in addition to, other layers being, pushed on top.
Then, like, that's just kind of constantly happening. Um, that could potentially add to the oil content if it gets pushed down far enough. But
Hmm.
generally, you only see, like, they're called petroliferous, oil rich layers.
Right.
Um, if there is that really solid time of very little sediment deposition and just really concentrated uh, dead stuff, because if you have it even still surprises me how much things will get compressed, because you could have, like, say, like, for example, 100 feet of dead stuff before it gets compressed. That could be compressed by the time it's oil down to like a foot, a couple feet.
Wow.
Yeah, it's really
Wow.
crazy. And granted, that is, I don't have any, you know, there's no way to measure that. Things compact at different ways. That's how you get different, like, hardnesses of rocks,
Right.
or what's called induration, like how well stuck together are the pieces in the rock. Um, so that's just me kind of throwing numbers out there. But if someone were to tell me that 100 feet of sediment turn into this, 1 foot layer of rock, that would not at all surprise me. And so we're talking about, like I said, hundreds of thousands to millions of years of no sediment, just dead stuff falling to the bottom, then getting covered in sediment before that can all decompose as it would normally. So while the sediment is falling, there's obviously more, things in the water column dying and falling with the now sand or clay that makes up the layer on top of the
Right.
all the original dead stuff. But it's just not concentrated enough, and it doesn't hinder the stuff below it from being turned into the hydrocarbons.
Gotcha. Okay.
And then once, people find the reservoir in the rock, they drill through the cap layer and just basically suck up the oil. And that's how we get oil.
And this is the oil that, like, I put in my car.
Not directly.
It
So
goes through a number of processes, I assume, but like it gets
right.
there
And
eventually.
so yeah, the big thing with oil is that it is, like I said earlier, crude oil is what's usually called before it's refined, because generally oil has a good mixture of the different kinds of compounds that have between 6 and 10 carbons in a chain. Like I said, how propane is 3 carbons, basically the
Hmm.
equivalent of that, but between 6 and 10 carbons.
Okay.
So it has to be refined. There's different amounts and different kind of fuels. Like jet fuel has like a different ratio of, like the 6 carbon thing to the 8 carbon thing to the 10 carbon thing. They have different ratios depending on what you're using it for.
All right.
So that is oil slash petroleum. So the next one we're going to talk about, because it is fairly similar, at least in a lot of respects, not everything, but is much more similar than coal. So we're going to talk about natural gas next. So Mike, what do you know about natural gas?
Not a whole lot. Fracking comes to mind. I don't know if
It
that
sure does.
actually matches. I believe, and I might be way off base on this. I believe hearing that the actual like burning of natural gas, it might be better for the environment than the burning of like oil or coal. Not that it's good, and not that
Hmm.
the process of getting that natural gas is all that safe, but like just like the strictly apples to apples, the burning of each of those fuels. I feel like natural gas is is better for the environment, but I don't like. I have always in my head kind of equivocated natural gas and just like petroleum oil without really considering the differences.
Okay. We will definitely talk about it being cleaner or not in a little bit, but that is pretty fair. It is very commonly associated with petroleum oil.
Hmm.
But natural gas is mostly used these days for heat. People will burn it, for like their furnace in their house. That's mostly what it's used for.
Okay. Is there a
Um,
reason for that it's not used in like cars or jet fuel or anything? Like, is there a particular reason it's better for that?
so all of the energy, well, yes, for this next moment that I will talk about here. So, natural gas, unlike petroleum, which I said was a mixture of mostly high carbon compounds, is almost entirely methane,
Hmm.
which only has one carbon. And the more carbon something has, the more energetic it is when you burn it, which is why high octane fuel is good for things like race cars, because when you burn an octane, which has 8 carbons, it is much more energetic than when you burn methane, just because there's more bonds to break, which is how you
Right.
get the
Okay.
energy.
Okay. So the more bonds that you're breaking, per atom or per molecule, the more efficient you're going to be, more explosive you're going to have of a burn.
At least the more total energy you will give off.
Okay.
Because in some chemical reactions, it could happen over a longer amount of time, but technically be a higher amount of heat if the reaction is just slower to happen.
Right. Okay.
But yeah, so there's just many more bonds to break, which give off energy with the high carbon content molecules as opposed to methane, which is, like I said, what natural gas is almost entirely. So it is formed very similarly to petroleum, but the gas parts separate out when the oil becomes more liquidy like that. The more dense and more heavy, so like the higher carbon content molecules, like the octane, will become more liquidy, while as ones that happen to break down into methane instead will turn into gas, because methane is very hard to turn into a liquid. Much harder
Oh,
to
is it
turn
really?
into a liquid. Yeah, just
Huh.
because it is,
I guess that
just
makes
because it's
sense. I just never
smaller.
thought about it.
Yeah, I mean, you can still do it given enough pressure, but it is much harder to turn into a liquid. You need a lot more pressure to turn into a liquid than you do with propane or butane.
Hmm.
Um, but yeah, so it will essentially, as oil forms, like we just talked about, there will frequently be sort of a bubble on top of the oil bubble made out of natural gas, mostly methane. So when they find that reservoir, that bubble of oil, they can sort of suck out the gas part first, and then not the and then after they're done with that, take out the liquid part. Or I'm sure there's some way to do both at the same time.
That really is cool, though.
Yeah, like all of the engineering that goes into oil extraction is really interesting and really, it is really just a marvel of engineering. I just wish that it did something different. Um,
Right. Like, we can separate out the good hard work that engineers have done to do this from the some of the consequences of that.
right. Uh, and like so that's not the only way that natural gas can form. It can form by itself, typically in smaller areas than a big reservoir, basically a big lake. Which, like, the petroleum reservoirs can be like the size of like a small to medium sized city.
Wow.
Which,
Really?
like, well, just because, think about it, if you've got billions and billions of things falling to their death over hundreds of thousands to millions of years, that covers a pretty wide area, you know.
No, that makes total sense. Just when you put it like that, like that's a huge.
Hmm. So sometimes if they're smaller than that, but still do happen to break down in a way that makes, these usable hydrocarbons, they will sometimes turn into natural gas and all break down completely into methane. So you can get methane without petroleum, but these days it is much more common to get natural gas while getting petroleum, with the exception of doing things like fracking. So for those not aware, fracking is basically you pump water, um, with really high amounts of pressure, and also usually some chemicals to help break through the rocks. We pump it into the rocks and fracture the rocks, is what's called fracking. Um, and by fracturing the rocks, you free up some of this trapped methane, which there might not be a big bubble of, but there might be lots of small bubbles in just this entire unit of rock. So if you break up the rock, the methane will take the easiest way out, which then is through the water that you are putting into that rock, and then you can later extract the methane from the water to use as fuel.
Okay, and so like that all sounds perfectly great. We've got water, water's clean, we drink water, and we're getting methane out the same way that we would otherwise. It's just now we're concentrating it. So why is fracking such a big thing? Why do people yell about fracking?
Fracking.
I say that like,
Mhm.
like I'm half asking like, stereotypical dumb guy, but I'm also like, like I'm aware fracking is generally seen as, horrific for the environment, but I don't quite understand why, other than like, poisoning the water supply possibly. But I have accepted that it's bad, but I'd love a breakdown as to why exactly fracking is such a problem.
That's the biggest thing, is because some of the chemicals that they put in the water to help break through the rocks and make the methane more stable as they're extracting it are pretty nasty.
Okay,
And
like what kinds of chemicals?
off the top of my head, I don't know. They're just generally things that aren't easily broken down by nature, and things that tend to be rather toxic to humans.
Okay.
So if the fracking company is responsible and avoid hitting an aquifer, which is where the groundwater essentially, um, then it's really generally okay.
Really? Okay.
However, if the cost of them screwing up is really really bad.
So it's a little bit of a cost benefit. You get some moderate benefits if done properly versus disastrous consequences if a mistake was made. And I'm imagining a mistake would be rather easy to make. Like it's not like it's got to be a series of colossal screw ups in order for that to happen.
Not like a series. Like you could screw up once and have it be real bad. How hard it is to screw up that once, I don't honestly know.
Okay.
I've never worked in like the energy side of geology, um, but a couple other things are just like the general blanket statement that like we shouldn't be extracting more fossil fuels from the ground to begin with is kind of an argument against fracking.
Mm-hmm.
And then also we get a good amount of natural gas from extracting oil, which we're doing anyway. So it's like, why do we need this extra thing when it has such a terrible cost if you screw it up?
Right. And that makes total sense, just understanding. I guess I never quite understood that, like with oil and petroleum, that was more in the ocean, which is, far away from human population centers.
Yes and no. So it form so both of these form in the ocean,
Mm-hmm.
but the ocean doesn't always stay where it used to be,
Right. Okay.
which is why places like North Dakota and places like Texas are really have a ton of oil, because they used to be oceans, really really productive oceans with lots of microorganisms, um, that are now on land and just much more convenient for us to get the oil from them now.
Okay.
So that more or less. Oh, actually, so bringing it back to why it's generally cleaner than burning gasoline or any derivative of petroleum. So similar to how one carbon, methane, burns less energetically than octane, which has 8. If you burn methane, you form one carbon dioxide molecule out of it. If you burn octane, there are 6 carbons there. That creates, or I'm sorry, octane has 8. There are 8 uh, carbon atoms there. That creates 8 carbon dioxide molecules.
Oh,
So
okay. So I
per
mean,
molecule that you burn, you create less carbon dioxide.
And I assume that we'll get there in the climate change episode, but like carbon dioxide, no bueno for the atmosphere.
Right. And methane is infinitely
Even worse.
worse.
Yes.
Well, I shouldn't say infinitely. Like,
Yeah.
and an order of magnitude worse, or more effective as a greenhouse gas than carbon dioxide is. So if you're gonna have one or the other in the atmosphere, it should be carbon dioxide. But still,
Preferably nitrogen.
the methane in the rock isn't gonna go anywhere, so it's not really a concern for it getting in the atmosphere. But if you take it out and burn it, then that puts the CO2 in the atmosphere.
Right.
So that is generally why natural gas is quote unquote cleaner to burn than like gasoline, which, like I said, has carbon molecules of between 6 and 10 carbon atoms. And I think like per like unit of heat or energy that you get out of burning methane, the returns diminish on the amount of energy per carbon molecule or per carbon dioxide molecule it produces as you go up.
Huh. That I would love to know how that happens.
Um, well, so basically, so if you have one carbon atom, right, it can have four hydrogen atoms around it.
Right.
Whereas if you have two carbon atoms, one of their bonds is taken up by the other carbon, which means each carbon can now only have six, or each carbon can only have three hydrogens around it. Instead of, if they were separate, they each could have four. So there are less total bonds per carbon as you go up and have more carbons in the chain.
Mm-hmm.
So that just means less atomic bonds to break per carbon, which is where the energy comes from. So it is less efficient than burning methane. At least if all you're worried about is energy per carbon dioxide molecule.
And this is all going back to natural gas, correct?
Yes.
All right.
So that is petroleum and natural gas. So the third fossil fuel that we're going to be talking about is one that gets talked about probably more just because it is much more, people have made it much more political. And that would be coal. So Mike, what do you know about coal?
So my understanding of coal, yeah, I believe it's solid as compared to the other two, which were like, liquid gas, depending on the circumstances.
Right?
Um, it's solid. I know that it is like coal mining is a thing, and just like going in and being a coal miner can be dangerous, even if
Mm,
like there's not a collapse, like just what it does to the air. It will give people black lung.
right?
I know there's a term that gets bandied about called green coal, and I remember one of our mutual
Or
friends, Morgan.
clean coal, I think
Is it
is.
clean? Clean. Yeah, I believe. Yeah,
Yeah.
maybe that's right. Clean coal. And I remember one of our mutual friends, Morgan, a number of years ago, like yelling at, like I was not saying that, she was like yelling at me as a proxy for whom she was actually talking to. That clean coal is not a thing. And I am in no position to say I believe she's right because she would know these kinds of things. But yeah, it is solid, used in trains, I believe. I
Okay.
just have like I have the old school imagination of like dude with a shovel, like shoveling coal into a train furnace. But yeah, that's my rough understanding of coal, is that there's no real such thing as clean coal. It is rather dirty. I believe it's made of carbon, which would kind of go with the theme here. For some reason, carbon's definitely
Hmm.
sticking in my head with that. But that's most of what I understand about coal.
I mean, that's more or less correct. There is really, our friend Morgan is correct. There is really no such thing as clean coal. Um, I don't really know how that ever became a thing. I think it just sounds kind of nice. People
It's a
want
thing
to
that you can
believe
tell
that it's
people.
cleaner than
Yeah.
it is, but like it's not. Um, so things for what coal is used for. in our society is previously it was used a lot for heat, particularly in like pre-electric times. People would burn it in their house for heat and to boil water and stuff like that. Nowadays, it is almost exclusively used for electricity production in power plants.
Oh, okay. That actually makes sense. I never thought about that.
Yeah, so basically how power plants work is they burn a bunch of something. You could do it with wood, but it's much less efficient. Um, but you burn coal that heats up a big tub of water. As the water evaporates, it rises and turns essentially a windmill inside the big tower of the power plant. So all the stuff you see coming out of like a power plant is just steam.
So,
And the turning of the windmill generates electricity just like a wind turbine out in a field would.
okay, so once again, for those that don't know, I'm the dumb guy in the podcast, but this this sounds like wind energy with extra steps.
You are absolutely correct.
Okay, how does that work?
It is much I shouldn't say much. It is generally more efficient in the sense that like you can generate a larger total sum of power more quickly
Okay.
because the steam rising moves faster than air will or wind will sort of on its own
Okay.
in
Well,
that sense.
that
Um,
makes some amount of sense even if
and also
wow.
as a side
Wow.
tangent, that nuclear power plants work fundamentally the exact same, except you're just doing nuclear things to heat up the water instead.
Huh. Okay.
So like the steam coming out of like a nuclear power plant, which you and I have seen a bunch of in Oswego, New York. Um,
Yes.
so that's just water vapor. There's nothing inherently wrong with that water vapor because the nuclear material is completely separate from that water,
Right. I would
obviously,
love to
or else that'd
have
be really bad.
I would love to have an episode on nuclear power because this is something I feel like I know a little bit about and have some thoughts on, but they're
We
probably
can
not as
rope
well
that into
developed
the
as they
to
should
the
be.
eventual climate change episode.
I am looking forward to that because nuclear power is something that I have some thoughts on.
Yeah. um, but yeah, so coal is fundamentally different from petroleum or natural gas in something that you hit on very nicely, in that it's solid. Coal is actually a rock. It is a type of rock.
Okay.
Um,
That makes total sense. Once again, just never
mhm.
thought about it like that.
And it is unlike petroleum and natural gas. It is formed from plants, almost exclusively on land. So, and also almost exclusively from two geologic periods, the Carboniferous period and the Permian period. Total stretch of about 100 million years of time, from about 360 or so to 252 million years ago. About 90% of our total coal comes from those two periods.
Hmm.
And
That's across
it's
the world or just in the United States?
across the world.
Okay.
It's called Carboniferous period for a reason. Uh, it was called
Yeah.
that because that's where
A lot of carbon.
the British people, carbon is what they called coal. It's where they got all their coal from. So they called the units that they associated with that time, or the time associated with those units, the Carboniferous period. So back in these periods, especially the Carboniferous, less so the Permian, but these is still sort of applied. That there were gigantic, like almost planet-wide swamps. Basically, if it was like land surface, um, particularly by the coasts, but it was all swamp and forest. And there were lots of things dying. Swamps are almost always a great place for things to get preserved, for the same reason that the bottom of the ocean is. That there's just not a lot of oxygen in swamp water.
Mm-hmm.
Because there's so many things falling in there and dying, that when things decompose, it absorbs oxygen from the water, and then but without oxygen, things can't decompose. So more things just fall, and it drops oxygen even lower, and things get preserved beautifully. That's where some of our best like mammoth, full mammoth skeletons are, and with like organs and things intact they're from swamps.
That's wild.
Yeah.
Gosh.
And but there's also some weird things that went on specifically around this time that add to this and why it's so good. Just like, again, the planet-wide swamp/forests. Obviously, that's great for it. But another thing is that it was around this time that plants evolved a compound called lignin, which is a hydrocarbon, or I guess a carbon-based molecule that they use in their cellulose to give them structure. Especially woody plants, like trees. They evolved the way to develop, or to just make this compound. And obviously, because it was brand new, no organisms had ever made it before, nothing had yet evolved to be able to break that down once that tree died. So there were trees dying, but the fungus and bacteria around at the time couldn't eat the dead tree. So it just sat there.
Okay.
And piled up and piled up and piled up. And because also they fell into the swamps, which were really good at preserving things anyway, it is a perfect scenario for preserving those trees. And then another thing also is that because there's so many plants around, that means that there's a lot of oxygen in the air during the Carboniferous period. That was when we're, very confident that atmospheric oxygen was at its all-time highest level. Lots of oxygen and lots of foresty material means lots of forest fires. Lots of forest fires means lots of naturally produced charcoal, which even today is extremely hard for anything to break down and decompose. Charcoal is basically already coal.
As you said that, like, I had one of those things where it's like, I wonder how long everybody else knew this and I was in the dark. Like, coal and charcoal, like, the word coal is in charcoal. I never made that connection, never realized it.
Mm-hmm. It is much less concentrated.
I'm just such a moron.
Charcoal is much less concentrated carbon than coal proper is, but it is still, relatively concentrated and hard to break down. So the charcoal would then, burn and fall into these swamps to then just become this giant mass of carbon building up with nothing to break it down. And this just made a extremely good perfect storm to produce massive amounts of coal the planet over. And eventually that would just get buried, as things do. And eventually, over time, hundreds of millions of years later, after it got buried, it would be uplifted by like a mountain building event, or eroded down to expose the coal. And then once we figured out, okay, there's coal in this area, we started digging around underground in mines and things for it. And that's how we get coal mines and things like that today.
Okay.
So that is how, obviously, there are coal that has formed in almost every period, realistically. You can actually go and find places today where coal is forming in things like swamps. And
like
peats.
You like
the very first baby steps. Very first baby steps of coal.
Right, okay.
And so there's actually different kinds of coal that vary based on their concentratedness, their concentration, that's the scientific word, of carbon. So the least one is called lignite, because it's made from lignin.
Mm-hmm.
Makes sense. Which is really low grade, meaning it hasn't been heated up all that much. It's honestly kind of just really flammable dirt, realistically. It's not really lithified at all. In total, it's between 25 and 35% carbon. total.
Mm-hmm.
The next one up is called sub-bituminous coal.
So bituminous?
Right, because the next one up is called bituminous. So
Is there any
it's
relation to butane? Like that sounds close.
nope, it's spelled BIT instead of
Okay,
BUT.
gotcha.
Um, but yeah, I don't know the origin of the word bituminous, but might be something fun to look up eventually. I don't know.
Yeah, another time.
But sub-bituminous is more solid and lithified than lignite is, and it's between 35 and 45% carbon. Moving up, you get to bituminous coal, even more hard, even more lithified. And the range on this one extends quite a lot. It's between 45 and 86% carbon. I don't know who decided these rules. They seem pretty arbitrary to me, but whatever.
Hey.
And then the most concentrated form of coal is called anthracite coal. Um, and that is between 86 and 98% carbon.
86 and 98% carbon. Wow. Is it
Yes.
like what happens if there's more than 98%? Is that just not a thing?
Then that becomes something like graphite.
Oh, okay. It's a little pencil lead.
Right. So graphite is pure carbon. However, it is the bonds between the hydrogen and the carbon that make it flammable and good for burning.
Mm-hmm.
So if there's no hydrogen there, it's very, very stable. Graphite is basically not flammable at all.
Hmm.
Uh,
That's good to know as a teacher who's around pencils a lot and, some unstable kids. But okay.
but yeah, so those are different kinds of coal, and that just depends on like how deeply it got buried, essentially.
Mm-hmm.
And so that's coal in a nutshell. So I kind of want to close this up by saying like, okay, so we've talked all about these hydrocarbons, and we all kind of know that burning hydrocarbons is bad. We've talked about that quite a bit so far in this episode. But like, why? Why is it bad? And the
And
obvious answer that most people know is that because it puts carbon dioxide in the atmosphere.
that was the answer I was going to give.
But as we sort of talked about, carbon dioxide gets put in the atmosphere all the time. Um, these things like the forest fires that I was just talking about, that must have put a ton of carbon dioxide in the atmosphere. You're burning a bunch of trees, burning pretty much any living material in general will release carbon dioxide.
Right?
So why is this bad specifically? So in nature, these these hydrocarbons, whether it's coal, natural gas, or petroleum, that we take out and burn, would have stayed there, inaccessible to the surface, for millions and millions more years. And so by bringing it up before it's ready, essentially, before nature is ready for it, more accurately, we are artificially increasing CO2 that way, because it would come up by itself in due time. Like I guarantee it. Whether it's
Mm-hmm.
a million years from now or 500 million years from now, that carbon that is stored underground in these various fossil fuel ways would have been brought to the surface by some means at some point, and then been put back into the carbon cycle to be taken up by a plant eventually and working in the cycle like that again.
Right. Is it like a naturally occurring process, though?
Exactly. And by bringing it up too early, we're increasing that carbon dioxide content more quickly than nature can adjust if it was just left to do it on its own accord.
Mm-hmm.
And so there are times in history, and this is going to be a little prelude to our climate change episode, where, uh, one of these massive coal seams, we think, caught on fire. And many, many, many things across the world died.
Just from that, just from like, what are the reservoirs of coal catching on fire?
I mean, not just, but we're pretty sure that was a very large part of it. And
Right.
this coal seam, we're pretty sure was like the size of several Eastern European countries.
Oh goodness. Okay.
Um, yeah. So pulling that carbon out of the rock before it is ready too quickly is very bad for essentially everything that lives on the planet.
And does that kind of wrap up the kind of our oil episode, our oil, natural gas, and coal? Does that kind of put a button on everything we need to know heading into our climate change episode?
I think so. Like you said at the beginning, it's kind of hard to know, so to really understand climate change without understanding sort of what we're actually doing. And so, even though it might have just sounded very obvious, where it's like, okay, we're bringing carbon out of the ground and putting it into the air, but a lot of people say like, oh, climate change, the stuff that we're seeing is just what nature would do anyway. No, no, it's not. In fact, yes, we are. Even before we started mucking with the atmospheric carbon levels, we were in like an interglacial period caused mostly by the Himalayas.
The Himalayas.
Um, well, I should say a lot of the glaciers were caused by the Himalayas
What do you mean
because
caused by the Himalayas? Like what does that mean?
side tangent. So, um, when certain types of rock erode, they suck carbon dioxide from the atmosphere.
Okay.
Just in the way that they weather it, the chemical reaction that happens absorbs carbon dioxide and takes it out of the atmosphere. When the Himalayas rise, that is a lot of rock to be eroded. And so that's what a lot of people sort of think might have kickstarted like the Ice Age. Things have been getting gradually
Huh.
cooler for a
Okay.
long time before that, but that's what some people think really kickstarted it, and like the massive glaciations we saw during the Ice Age. Some people also think that like the Himalayas rising slowed, which is something that partially contributed to the current interglacial cycle that we are in.
Wow. You blew my mind at the end of the episode.
Yep.
All right. So like that is about it on what we have here for oil, coal, and natural gas.
I think so.
Wonderful. Well, thank you, Gavin, for breaking that down. That was you know, like I said, kind of at the outset, we've all kind of heard of natural gas. Going back to, at least for me, elementary school. Um, and like it was bad. Burning natural gas is bad, and it releases carbon dioxide into the air. But just getting sort of that breakdown of the differences between the different kinds of oils. What's the proper term to refer to all three of these: oil, coal, and natural gas?
Just fossil fuels.
Fossil fuels. You know
Yep.
what? I knew that. I swear I knew that. Um, but just like hearing the breakdown of what makes them different, and yet what makes them all the same, what makes them problematic is really helpful for me as we go into our next episode. So thank you very much, Gavin, and I look forward to seeing you next week.
Absolutely, buddy. See you then.
Awesome. Take care, everybody, and we will see you all next week with another episode of I Wish You Were Dead, a podcast about things that used to be alive. Take care, everyone.